Dear students, welcome to today's lecture. So here I am going to present the Baire Category Theorem. Actually, there are many versions of Baire Category Theorems, and this is the one of them. So here in this presentation, I mainly talk about the Baire Category Theorem, which is for metric space. So this says, so first state the theorem. So let XD be a complete metric space. So let UN, so n equal to 1 to infinity, be a collection of open dense sets. Obviously, they are open and dense in X, right? Now, this theorem says then the intersection n equal to 1 to infinity of UN is also dense in X. In other words, this theorem says if X is a complete metric space and if UN is open in X and UN closure equal to X for each n, then if you take the intersection n equal to 1 to infinity UN, then it is also dense in X. That means its closure is also X. So this is the statement of this theorem. So now I shall prove this theorem. So here is the proof. So first of all, so we can see one observation. So since each of my UN is dense, so we can apply the definition of dense. It says for any open set, set W in X, we have W intersection UN is non-empty, right? So this is the definition of dense set. Now we can talk about something more than that. What is that? See, each UN is also open set, right? And W is also an open set. Therefore, U intersection W is not just non-empty, it is also an open set. Therefore, we can say W intersection UN is a non-empty open set in X. Right? Okay. Now what we need to prove? We need to prove that intersection of all of this UN is dense. That's mean if we choose any arbitrary open set, say B, then we have to show that B intersection, that intersection of UN is also non-empty. So we choose let B be an arbitrary open set in X. Now we claim that intersection of I equal to 1 to infinity un, and if you take intersection this set with B, that is non-empty, which is equivalent to saying that intersection I equal to 1 to infinity un is dense in X. Okay. So there are several steps of the proof of this theorem. So here is the step 1. So for the first step, we choose the open dense set U1 and we choose W as the open set B. That's when we shall apply this one. Okay. So here, so for the step 1, this W is my B and this UN is my U1. Okay. So that's mean so we can use that one since U1 is an open dense set in X. So we can say that B intersection U1 is a non-empty open set. Right? We have already observed this. Now since this is non-empty, so we can choose one element, say x1 in this set. So E1 intersection B. Okay. Now we apply that this set is also open. Now since U1 intersection B is open, so there exists an open ball, say BD x1 comma R, such that this open ball with centered at x1 and with radius R subset of U1 intersection B. So what do you mean by open ball? So this means it is the collection of set all X in X such that in the set X such that D of x1 comma X it is strictly less than R. Okay, so this is the definition of open ball. Fine. Now there is no condition for the R for this radius R. Now we choose R1. So let R1, we choose R1 such that it is a minimum of my R and 1. That is, we will choose R1 such that it will be less than R as well as R1 will be less than 1. Then the ball R1, that will be subset of the closed ball, that will be the subset of the previous ball of radius R, and that is subset of U1 intersection B. Now what do you mean by the closed ball? Again, I can define that here. So this closed ball means X such that D of X1 comma X, it is less than equal to R1. Now it is easy to see that, and this is my X such that D of X1 comma X, it is less than R. Right? Now since R1 strictly less than R, so this inequality follows. Right? Okay, this part is done. Now this is all about the step 1. Now we will go to the step 2. Now in the step 2, we will use the fact of step 1. So this is my step 2. Now for step 2, we choose this ball as my W, as W in step 2. Okay. So here is my step 2. So since U2 is an open dense set in X, so we can say BD that X1 comma R1 intersection U2 is a non-empty open set in X. Right? It is clear. Since U2 is dense, so the intersection of this open ball with U2 is non-empty, and since both are open, so their intersection is open. So this is fine. Now again, we can choose X2 on this one. So let X2 belongs to this. X1, R1, intersection U2. Now we can use the property of the matrix space, that is the step 1. So we get, so we can write by similar argument as in step 1. There exists R2 less than half such that BD X2 R2 subset of the closed ball X2 R2. Now this is subset of BD X1 R1 intersection U2. Fine. See, this part is simple. I can explain again. Now this is my open set and X2 belongs to this open set. Therefore, we can have a ball with centered at X2 and with some radius say R. Now what we can choose? We can choose my new radius, so new ball centered at X2 and with radius R2, where R2 is less than half and R2 is less than of that previous R. Then we will have this ball, that is BD X2 R2 subset of the closed ball this one, and this is subset of this open set. So we are done, right? Now we can continue this process again and again. So we can continue recursively to get step n, right? So what is my step n? So this is the statement of step n. So since un is an open dense set in X, so there exists Rn less than 1 by n such that so this Xn belongs to this Bd Xn Rn subset of Bd closure Xn Rn, that is subset of Bd Xn minus 1 comma Rn minus 1 intersection Un, right? Is it clear the step n? So you can see that the step n is just the generalization of step 2, right? If you put here n equal to 2, then you will get here x2 and here r2, right? And here you will get x1 and here you will get r1, right? For n equal to 2, and which is the same as my step 2. Fine. Okay. Now you can see that this is a race and we never complete this race. That's mean we have step 1, step 2, step 3. Every time we are getting one number x1, x2, x3 and xn and so on. But it will never be completed. So that is the reason now we use the axiom of choice. So here we use the axiom of choice. So what is the axiom of choice? If you don't know, then I can state again. So which states, say informally, because it is not the formal definition. So it formally says, given an infinite collection of non-empty sets, it is always possible to make a selection of exactly one point from each set. That's mean, suppose you have a collection of infinite number of non-empty sets, then you can always choose one element from each of those sets and you can make a new set. Anyway, you can never complete this choice, but axiom of choice says you can have a set which contains exactly one element from each of those non-empty sets, even if the collection is infinite. Fine. Now by using axiom of choice, we can have a sequence xn. So by using axiom of choice, we have a sequence xn, right? And what is the property of this xn? We can write such that xn belongs to bd, that xn comma rn subset of bd closure xn again rn, and that is subset of the open ball xn minus 1 comma rn minus 1 intersection un. Okay, so if m bigger than n, then we can see my xm belongs to the ball of centered at xm with radius rm, right? And this is subset of again bd closure xm rm, right? And that is subset of bd xn rn, right? That implies we can say d of xm xn belongs less than rn, and that is less than 1 by n. And this is true for all m bigger equal to n, right? As you can write xm comma xn both belongs to that set bd xn rn. Is this fine? Okay. Now we claim that this will imply the sequence xn is a Cauchy sequence. Now claim the sequence xn is a Cauchy sequence. So why this is a Cauchy sequence? So we will prove here. So first of all, choose any arbitrary epsilon bigger than 0. Now we choose a large n such that 1 by n less than epsilon by 2. Now what will be my dxm comma xn? Now dxn comma xm, that will be, if you use the triangle inequality, that will be less than equal to dxn x, that capital N, plus dx capital N comma xm, right? Now if we choose my small n and small m bigger or equal to capital N, then that will be less than 1 by n plus 1 by n, which is less than epsilon. So you can write for all n comma m bigger equal to capital N, right? Why? Because if small n and small m bigger equal to capital N, that's mean that xn and xm both will be B, that is the ball centered at x capital N, right? Because we can write the region as xm and xn belongs to that ball BD x capital N R N. Okay. Belongs to B x n R n. Okay. Now this will imply the sequence xn is a Cauchy sequence. It is given that our metric space is complete, right? So we can use that fact. Since XD is a complete metric space, so we can say our Cauchy sequence, that is Xn, is convergent. So say Xn converges to a point X, which is in my metric space, right? Now there is a beautiful observation, which is for any natural number m, that xn, which is belongs to b d xn comma rn, right? That is subset of bd closure xn rn, that is subset of bd x m r m. This is true for all n bigger equal to m. Now that implies xn belongs to, so bd again, if we can take closure of xm comma rm for all n bigger equal to m, right? So after some stage, that is after the mth stage, all the xn belongs to this closed set. Now since bd closure xm rm, here we can write this fact, bd closure xm rm, this is a closed set, and xn converges to x. So my x belongs to bd closure xm rm, right? Now note that here we have taken this m is arbitrary but fixed, right? So therefore we can say x belongs to bd closure xm rm for all natural number m. That's when x belongs to bd x1 r1 as well as x belongs to bd closure x2 r2 and so on. Fine. Now if we go to the nth step, we can see that, see, it is, you can see that this is subset of un, that is bd xn rn is a subset of un, right? So we can use that fact here, since bd closure xm rm is subset of um for all m belongs to natural number, that imply x belongs to um for all m belongs to natural number, right? So x belongs to um for all natural number n. Now that implies x belongs to the intersection of I equal to, or you can say n equal to 1 to infinity un, right? Now again use this observation here. In this case my m is arbitrary but fixed, right? So this m can be 1 as well. Now if we choose my m equal to 1, that's mean then we will have x belongs to bd x1 r1. Now by taking that m equal to 1, we get x1 belongs to bd closure. So x belongs to x1 r1, right? So just we use here m equal to 1. So use only this fact. Okay. Now what we know about this ball? Now we can go to the step 1. Now this is my step 1. Now here you can see that this ball, this closed ball R1, this closed ball is actually subset of this intersection. That's mean this closed ball is subset of B as well, right? Now X belongs to this closed ball. So X belongs to this closed ball and this closed ball is subset of this ball, right? Therefore, now since BD closure X1 comma R1, this is subset of B, that implies X belongs to B, right? So X belongs to B as well as X belongs to this intersection. Therefore, X belongs to the intersection of I equal to 1 to infinity u. So n, can write here n intersection B. In other words, for the arbitrary open set B, this intersection n equal to 1 to infinity un with B is non-empty. That implies that's 1 un is dense in X, and we are done. So this is the proof of the Baire category theorem, and now we shall see few applications of this theorem. So let's start with a simple example. So we can write problem 1. So is there any function f from R to R, that is set of real number to the set of real number, which is continuous only on irrationals. That's mean which is continuous on irrational numbers and discontinuous on rational numbers. Since the point of discontinuity is the countable set, so we can give one example. So here I am giving one example. Obviously this is not the only example, so there are several examples as well. So here is the solution. So first of all, since Q is countable, so we know it is a infinite countable set, right? So we can write Q as a list of a sequence. That's mean we can write Q as a sequence, that is x1, x2, x3, dot, dot, dot. Why we can write Q as a this type of infinite sequence? Because Q is countable, so it is an infinite countable set. So there is a bijection from N to Q. Suppose f is the bijection from N to Q, so my x1 is just my f of 1, x2 is just f of 2, and so on. Right? So we can write Q as a set of a sequence. Fine. Now we can define a function. So let f R to R be defined by so f of x equal to 1 by n if x is xn, which is a rational number, and we will define equal to 0 if x not belongs to rational. Now we prove that f is continuous at irrational numbers and not continuous at rational points. So first of all, we show the discontinuity. Claim f is not continuous at xm, where xm is an arbitrary element of Q, that is a rational number. So first of all, let x equal to xm, right? Then f of xm, what will be my f of xm? It will be 1 by m, right? By the definition of the function. Now we define another number or another sequence, say Rn, which is my xm plus root 2 by n. Now obviously you can check that xm is a rational number and n is a natural number, right? Therefore this is a irrational number, so not belongs to Q, right? So that implies the sequence Rn is a sequence of irrational numbers. Irrational numbers, and you can easily check that Rn converges to xm and Rn converges to xm as n tending to infinity. Right? This is clear. Now suppose f is continuous at the point xm. So if f is continuous at xm, then by the definition of continuity, we must have f of Rn should be converges to f of xm. right? So this is the definition of continuity, right? So Rn converges to Xm, and if f is continuous at Xm, then f of Rn converges to f of Xm. Now what is my f of Xm? This is just 1 by m. Therefore f of Rn converges to 1 by m. So f of Rn converges to 1 by m, this number. So if f is continuous at Xm, then f of Rn converges to Xm. But what is my f of Rn? Now since Rn is irrational, therefore f of Rn equal to 0 for all n. Therefore the sequence f of Rn is nothing but a zero sequence. And hence converges to 0. Converges to 0. That is f of Rn converges to 0, which is not equal to 1 by m, which is my f of Xm. That implies f of Rn does not converges to f of Xm, though Rn converges to Xm. Right? Now this is a contradiction. This is a contradiction. Therefore, f is not continuous on rational points or rational numbers. Fine. Now we prove that f is continuous at all the irrational points. Now this is my next claim. F is continuous on irrational numbers. That is, we choose, say let A be an arbitrary element of R minus Q, that is irrational number, and we prove that F is continuous at the point A. Okay. Now we prove epsilon delta definition to prove this continuity at A. So first of all, we choose a arbitrary number epsilon bigger than 0. So choose an arbitrary number epsilon bigger than 0. Right? Now depending on epsilon, we can choose one n natural number. So then choose a natural number n such that 1 by n is less than epsilon. Now we choose an open set. So let U equal to R minus that finite set. So x1, x2 up to xn minus 1. Now obviously this is an open set, right? Because this is a closed set and this is the complement of a finite set. So U is an open set in R. So then U is an open set in R. Now obviously U contains A. Why? Since A is a irrational number, right? So A not equal to xn for n equal to 1, 2, up to n minus 1, right? Therefore, we can say A belongs to U. That's mean U is an open set in R containing A. Thus, U is an open set in R containing A. Right? Okay. Now, what is my f of A? So here f of A equal to 0 by the construction, or you can say by the definition of my function. Now choose a arbitrary element x in U. So x is arbitrary. Okay. Now there are two possibilities. This x can be rational or can be irrational. Now if x belongs to rational, that is if x is rational, then x will be some xn for some n, right? And obviously where n will be bigger equal to number n, capital N, right? Because x1, x2 up to xn minus 1 is not in U, right? Now if x is some xn, then that small n should be bigger equal to the capital N, right? Now then f of x will be, now since x equal to xn, so by the definition of my function, this will be 1 by n. Now again, since that small n bigger equal to capital N, so this 1 by n less than equal to 1 by capital N, and we know this is less than epsilon. And in this case, we can write mod of fx minus fa, and we know this is fa is 0, so it is just f of x, and this is less than epsilon, right? Why? Because fx is positive. So here f of x is positive. Fine. Okay. Now what if x is a irrational number? Now if x is an irrational number, then f of x equal to 0. Now that implies mod of f of x minus f of a, and both are 0, so it will be 0 minus 0, so it will be again 0, right? So it is always strictly less than epsilon. Therefore, we can say mod of f of x minus f of a less than epsilon whenever x belongs to U. And this proves A is continuous at A. Now this proves F is continuous at A. Now since A is arbitrary, is an arbitrary irrational number. So we can say f is continuous on irrational numbers. Okay, so this is the proof of the problem 1. Now, if you are undergraduate student and if you don't get the continuity, that's mean if you know only the epsilon delta definition, then also it is fine. So we can use that epsilon delta definition here as well. How? So this is not the part of this proof. So you can see, since A belongs to U, right? And U is an open set. So there exists a delta bigger than 0 such that neighborhood A minus delta comma A plus delta subset of U, right? Because U is an open set and A is a point of that open set. So we can have this neighborhood. So this is a definition of an open set. Thus, for the given epsilon greater than 0, we have that delta. So there exists delta greater than 0 such that mod of f of x minus f of a less than epsilon whenever mod of x minus a less than delta, or x belongs to a minus delta comma a plus delta, this one, right? Because if x belongs to this set and this is subset of u, then x belongs to u, and we have already proved that if x belongs to u, then f of x minus f of a less than epsilon. So this proves the continuity of the function f at a, right? So this completes the proof of this function. Now there is one question come from this question, that is, so we have a continuous function. So sorry, we have a function from R to R which is continuous on irrationals and discontinuous on rationals. So what if we ask in other way, that is there any function f from R to R which is continuous only on rationals? That's mean, is there any function f from R to R which is continuous on rationals but discontinuous on irrationals? Is it possible to find? Now the answer is actually no. You cannot find such a function. And the proof is little bit tricky, and we have to use the Baire category theorem to prove that result. So now we shall prove that result. And here is the statement. That's when we have problem 2, and we ask, is there any function f from R to R which is continuous on rational numbers and discontinuous on irrational numbers? And the answer is no. And here is the explanation. So first of all, we assume, if possible, let f be a function from R to R which is continuous on rationals and discontinuous on irrationals. So we assume f is such a function and we will get a contradiction. Now before that we need the concept of diameter of a set. So though it is clear, still I want to give the definition. So for a set U subset of R, the diameter of U is defined by the supremum of all the distance of U1 and U2 where U1 and U2 belongs to U. And we will denote the diameter of U as this. Fine. Now we choose a set UN. So let UN be the set which is union of all open sets U of R such that the diameter of U, not diameter of U, diameter of f of U less than 1 by n. Now you have to concentrate on the set UN. So we are not saying that the diameter of UN is less than 1 by n. We are not saying that. We are saying that UN is a open set and which is a union of all the open sets U of R such that diameter of the f of U, diameter, not, we are not saying the diameter of U, we are saying that diameter of f of U is less than 1 by n. Okay, so this is my set. Anyway, if still this definition is not clear, it will be cleared later, because when we use this one, that is UN, then you will get a good idea about this set. So for a timing, you just remember that UN is the union of all open sets U such that diameter of f of U less than 1 by n. Remember that not diameter of U. It is saying that diameter of f of U less than 1 by n. Now my claim is, so if f is a function from R to R such that f is continuous on rationals and discontinuous on irrationals, then Q is equal to this intersection of 1 to infinity ui, or we can write here n, it looks better, 1 to infinity un. Fine, we will prove that Q equal to intersection of n equal to 1 to infinity un. So first we prove that Q subset of this set, and then we prove that this set subset of Q. So first we prove that Q, that is the set of rational number, or you can say the set of continuity, is subset of intersection I equal to 1 to infinity. I always write I equal to 1 to infinity, but it is better to write n equal to 1 to infinity un. Okay. So how to prove that A subset of B? So we will choose one element from the left hand side and we will show that that element is on the right hand side. Right? So we are then we will be done, right? So let R belongs to Q. Now we know that, so we assume that f is a function which is continuous on rationals, right? That's mean f is continuous at R, right? So what do you mean by continuity or continuous at R? That's mean for every epsilon, for any arbitrary epsilon, we can have a delta, right, greater than 0, such that whenever x belongs to that R minus delta, comma R plus delta, that is whenever x belongs to the delta neighborhood of R, then fx minus fr, their distance should be less than epsilon. And this is true for any epsilon, right? We can choose arbitrary epsilon. So now choose, since we can choose any epsilon, so we choose my epsilon equal to 1 by 4n. Why we will choosing that epsilon equal to 1 by 4n, we will see later. Now since f is continuous at the point R, so there exists delta bigger than 0 such that x belongs to R minus delta, comma R plus delta will imply mod of f of x minus f of R less than epsilon, and my epsilon is 1 by 4n. So it is 1 by 4n. Fine. Now we will assume this is my u. Now let u equal to this set R minus delta, comma R plus delta. And we prove that the diameter of f of u is less than 1 by n. Why that is true? Okay, so choose, so let x, y be any 2 point in u. Then what is my f of x minus f of y? Now if we use the triangle inequality, we will get this is less than equal to mod of f of x minus f of r, right, plus again f of r minus f of y, right? Now we use this part. So it is saying that here my x belongs to this delta neighborhood of R, right? Therefore, this part is less than 1 by 4n. And again, y belongs to the delta neighborhood of R. So this is again less than 1 by 4n. So we have 1 by 4n plus 1 by 4n, which is 1 by 2n. Now see, the right hand side is just in terms of n, right? It will not depend on the choice of x and y. Therefore, if we choose the supremum of x and y, which is in u, then we have f of x minus f of y. Still, instead of now less than 1, less than, we will have less than equal to 1 by 2n. Right? Now what is this term? That is the supremum of this. This is the definition f of u, right? So we can write diameter of f of u is less than equal to 1 by 2n, and this is strictly less than 1 by n. Right? Now did you get why we are using this epsilon equal to 1 by 4n? Okay, fine. Now, so that's mean R belongs to u and diameter of f of u is strictly less than 1 by n. Now that will imply R belongs to un. Why R belongs to un? So what is my u? Sorry, what is my un? So un is the, so we can recall the definition. It is, so un is the union of all open sets U such that diameter of f of u less than 1 by n. Right? Now here this u is open, right? And diameter of f of u is less than 1 by n, right? That's mean R belongs to U implies R belongs to un. Here U is a subset of un. Fine. So we have U subset of, sorry, we have R subset of un, and this is true for all n. So thus R belongs to un for all n, right? Since n is arbitrary. Now that will imply R belongs to intersection n equal to 1 to infinity un. Now what we have taken from for R, so we have taken R from Q, right? And we have proved that R belongs to that intersection of un. So therefore Q subset of intersection of n equal to 1 to infinity un. Now we will prove the converse part. That's mean, so now we prove that intersection n equal to 1 to infinity un, that is subset of Q. So again we choose, let R belongs to this set, right? That imply R belongs to un for all n belongs to natural numbers. Okay. Now we need to prove that R, that is f, is continuous at R, and then it will follows. Okay. So first of all, we choose to prove that f is continuous at R, we choose any arbitrary epsilon. So choose an arbitrary epsilon bigger than 0. Okay. Now we always have some natural number n, then there exists natural number n such that 1 by n less than epsilon, right? Now since that R belongs to un, since it is R belongs to un for all natural number n, and here my 1 by n less than epsilon, so R belongs to that un as well, right? Now since R belongs to un and un is the union of all the sets, all the open sets U, such that diameter of f of u is less than 1 by n, right? So therefore there exists an open set U containing R such that diameter of f of u less than 1 by n. Now you can ask why that set U will contain R. that is actually simple and trivial observation. Anyway, I will prove that one as well. So what is my UN? So UN is actually union of all the collection of open set U alpha where diameter of f of U alpha less than 1 by n, right? Now here we know that R belongs to UN for any natural number n. That's mean if we fix any n, then also R belongs to UN, which is union over this, right? Now since R belongs to union of this set, that imply there exists alpha of that index set such that R belongs to U alpha and diameter of that open set. So here f of U alpha may not be open. So U alpha is an open set, and diameter of f of U alpha is less than 1 by n, right? So we can take U as that U alpha, right? That's mean whenever R belongs to UN, so there exists an open set U containing R such that diameter of f of U less than 1 by n. Fine. Now what does it mean that diameter of f of U less than 1 by n? That's mean, okay, so this is not the part of my proof. So thus, for any x belongs to U, we have mod of f of x minus f of r. Now obviously this is less than equal to diameter of U, right? Because x and r both are in U. Diameter of f of U, right? And this is less than 1 by n, and this is less than epsilon. So therefore, thus for a given epsilon bigger than 0, there exists an open set U containing R such that x belongs to U imply f of x minus f of r less than epsilon. And this proves f is continuous at R. Okay, so we choose, so here we have chosen that R belongs to this intersection. Okay, and we prove that if R belongs to that intersection, then f is continuous at R. But we know that f is continuous only on Q. So R belongs to Q. That implies that intersection n equal to 1 to infinity un, that is subset of Q, right? So we have chosen R belongs to that intersection, and we find that f is continuous at R. Now since f is continuous only on rational numbers, therefore R belongs to Q. Therefore R belongs to that intersection will imply R belongs to Q. Therefore this intersection is subset of Q. And in the first part we also proved that Q is subset of this. Therefore we have Q equal to intersection n equal to 1 to infinity un, where un is an open set for all n, right? That's mean Q is written as intersection of countable number of open sets. In particular, Q subset of un, right? Now we know that Q is dense in R, right? Thus, that each of the open set, each un is also dense in R, right? That's mean each un is a dense and open in R, and Q is the intersection of this collection of un. Fine. Now we will use the countability of Q and we will get a contradiction. So first of all, since Q is countable, so Q can be written as again x1, x2, x3 in this way. It is as a set of a sequence, right? We have explained that. Now let another set Vn is my un minus singleton xn. So that's mean, see, we know that Q subset of un, right? So that's mean Q minus that singleton xn is subset of Vn. You can write un minus that xn, which is my Vn. This is true for all n. And we know that Q minus xn, that says Q is a dense in R. Now if you remove exactly one point from Q, then the resulting set is also dense in R, right? Now we know Q minus xn is dense in R for all n, right? So therefore, each Vn is also dense in R, right? So that's mean each Vn is an open and dense set in R. Fine. Now, can you recall the Baire category theorem? What does it says? Okay, we can recall the Baire category theorem, the first page, right? Now, this is the Baire category theorem. It says, let X be a complete matrix space. Now, here my R is complete. We know that it is complete, right? Now, this says if you have a countable collection of open dense sets, then their intersection is also dense in X, right? So, in our case, Here R is complete metric space, and this collection Vn n equal to 1 to infinity is a countable collection of open dense sets in R, right? Therefore, by the famous Baire Category Theorem, we have that intersection n equal to 1 to infinity Vn is dense in R. Fine. Now, what is my intersection? That is intersection of n equal to 1 to infinity Vn. Can it be dense in R? So let's check out. So intersection n equal to 1 to infinity Vn, it is just intersection n equal to 1 to infinity un minus singleton x. Okay, so that is intersection n equal to 1 to infinity un intersection that x complement, sorry, this xn, right? Xn complement. Now if we separate that intersection, so this un depends on n and also xn depends on n, right? So we have two intersection n equal to 1 to infinity un intersection n equal to 1 to infinity xn complement, right? Now the first part, that intersection we know, that is q, and for the second part we will use the De Morgan law, that is union of n equal to 1 to infinity xn and then whole complement. And we have seen that my q, so here intersection of n equal to 1 to infinity un equal to, we know that is q, and we know that q equal to my set x1 x2, this set. So this union is actually q, so it is q intersection q complement, that is empty set. Now this intersection is an empty set, so it cannot be dense in R. So that implies intersection n equal to 1 to infinity Vn is not dense in R. Now this is a contradiction. So we have chosen, if possible, there is a function from R to R which is continuous only on rationals. That is, we assume there is a function f from R to R which is continuous on rationals and discontinuous on irrationals, and we get this contradiction. Therefore, there is no such function f from R to R which is continuous on rationals and discontinuous on irrationals. So this completes the proof. Okay, hope you will enjoy this proof. So we will meet in the next lecture.